Start recording, please.
Great.
Meeting continue. Okay, everybody. So welcome to today's meeting of the Non-Commutative Geometry group in Prague. Today's speaker is Zhaoting Wei from Texas A&M.
Non-Commutative Geometry and Topology.
Texas A&M University Commerce, and he will speak about determinant line bundles and cohesive modules. So please.
Right, thank you for inviting. Yeah, today my talk is actually easy, and I hope it's interesting too. Yeah. So it's actually my understanding of non-commutative geometry, so how to do it. So first, let me see how to move it. Page down. Yeah, okay. For the outline, first we'll talk about coherent sheaves and their determinant line bundles. That is in the framework of commutative geometry. And the second part is cohesive module. That's maybe some of you have heard of that. That's non-commutative framework of the study of coherent sheaves. And last part is how to define and study determinant line bundles in the framework of cohesive modules. Okay, first, coherent sheaf. I think most of you know it. A sheaf of OX module is called coherent if it satisfies two conditions. First, there exists a finite local resolution. So that's first condition, local finiteness. And second is for any open set, any number n, any morphism O(n) to f in this open set, the kernel of this morphism is again of finite type. Is there any chat? Oh, you cannot see the slide? Oh, sorry.
I can see the slides. Rita.
Is there anyone else?
I can see the first slide, but I didn't. I imagined you had a next slide.
I only see the title.
Yeah, the title is
slide.
Okay, yeah. So let me see if I need to do it again. Yeah. And maybe I'm moving the wrong. Oh, this. Yeah.
Aha.
I'm moving the wrong thing. Yeah. I'm moving another file. Okay, so yeah, I think this is here. Coherent sheaves, two conditions. First, finite type. Second, for anything open, yeah, the morphism, the kernel of this morphism phi is also of finite type. And for our complex manifold, the good news is, of course, the OX, the sheaf OX itself, the structure sheaf itself is a coherent sheaf. So somebody asked why we need this, because the second condition before, it's not obvious that for anything, the kernel is any phi, the kernel of phi is still finite type. So it's not a very easy theorem, but it is true. But with this, we know that any vector bundles or locally free finitely generated sheaf is coherent, and the kernel, co-kernels, and finite direct sums of coherent sheaves are coherent. It's a very good category. Of course, not all coherent sheaves are locally free. So we have skyscraper sheaves and etc. Okay, so that's coherent sheaves. Then determinant line bundles of a coherent sheaf. First, determinant line bundle of a vector bundle. That's obvious, that's trivial. So just take the top wedge product of this vector bundle, we get the determinant line bundle. It's also a holomorphic vector bundle. So in this talk, we use the curved letter to denote sheaves and use the straight letter to denote the vector bundles. And the point is actually, it's a well-known point that for a coherent sheaf, we can define its determinant line bundle. Although the coherent sheaf F is not a vector bundle, but the determinant line bundle is a holomorphic line bundle. That's a well-known result for, that's a classical result for coherent sheaves. Let's see how to define it in the framework of commutative geometry. First, Zizigi theorem. That is, for coherent sheaf, there is always a bounded local resolution. We call it locally free resolution. And the point for this resolution is the length is finite. And of course, this only holds for singular space, non-singular spaces. If the space has singularity, then it's no longer true. And if the space is a projective manifold, then actually the resolution exists globally. But for non-projective manifolds, then yeah, maybe non-globally. Yeah. So Vazan gave a counterexample. Yeah. Okay, then with this resolution, how to define the determinant line bundle? The first step is for a locally free resolution, we just define the determinant line bundle locally on U by the alternative tensor product of the determinant line bundle of each of these components. And the point is, of course, this resolution may not exist globally and is not unique. So the point is, if we have two locally free resolutions, then on the overlap, we have a canonical isomorphism, just determined by the determinants by these resolutions, it's themselves. And we have a canonical isomorphism. Then using this canonical isomorphism, we can glue together the locally defined determinant line bundle to get a globally defined line bundle, which is the holomorphic line bundle. So that is how we define the determinant line bundle of a coherent sheaf.
Sorry, is it supposed to be numerical invariant, or I mean that when you say the determinant of F, it's supposed to be?
What do you mean by numerical invariant?
I mean that determinant of F is a vector, or?
Yeah, it's a vector bundle. It's a bundle. So I think that we can define from this, we can define further numerical invariants of the coherent sheaf. For example, the chain class, yeah.
I see.
Chain class, etc. But yeah, determinant line bundle itself is a line bundle.
I see. And if this determinant is zero, I mean the zero vector, is there any nice relation for F, or?
Let me see. Let me see. If the determinant line bundle is trivial, then what is the? Yes, I think there are a lot of special properties of this F if the determinant is trivial. But yeah, so yeah, maybe yeah, yes, but yeah, I cannot remember in full details. But yes, yeah, a lot of special properties. Yeah, if the determinant. Okay. So yeah, of course we cannot say that it's zero. We can say that it's trivial. It's a trivial line bundle. Okay. Okay. Yeah. So there are some comments. For example, yeah, we can further define, yeah, since we have the determinant line bundle, we can further define the first chain class. It's and maybe chain number of the coherent sheaf. It's an important numerical invariant. And further, we can define like the degree, the slope, and the stable conditions on coherent sheaves, yeah, from this. And we can also define the determinant line bundle of a bounded complex of coherent sheaves in the same way, just take alternative tensor product of the determinant line bundles. And of course, this whole process is definitely a commutative geometry process. It depends on the local definition, and globally we glue them together canonically. So yeah, it's very commutative geometry. Okay, so is there any questions? Other questions so far? Comments? Okay, so yeah, now let's go to the second part. Oh. How do you study this theory in the framework of non-commutative geometry? So the starting point in my mind is the Searle-Swan theorem. That is, on a manifold, there's a correspondence between vector bundles, C-infinity vector bundles, with the category finite generated projective modules of global sections of functions. this is the Zhaoting theorem. So we can transform the study of vector bundles to the study of projective modules. We can, we no longer need like transition functions and this kind of thing. But the correspondence theorem for holomorphic vector bundles is not that easy. So it's not true actually. So we cannot say that a holomorphic vector bundle on a complex manifold is one correspondence to finitely generated projective modules over global sections of holomorphic functions. That's trivially wrong. But we have
excuse me, can I ask a question?
Sure. Yeah, sure.
Well, it's true. It's not anymore true, but you could retrieve a local version of it, couldn't you? Of that.
Yes, locally it's true, but what we want is globally. So that's the point.
No,
so I think
but if it's true locally, then with the gluing procedure you cleverly described before, you can make a sense of it, where instead of taking the ring C infinity X, you take the sheaf of your X, and then you can play the same game, can't you?
What do you mean by play the same game? Could you say that again? If we are talking about holomorphic, if we are talking about
establish
holomorphic.
an equivalence between two categories, except that instead of having C infinity X modules, you have some more generalized notion of it, right?
Yes. So I think what you said is true. So if we have the category of holomorphic vector bundles and the category of finite generated projective sheaves over the sheaf of, but that is not what we want. What I want.
Okay,
what
sorry.
We,
because you said it's not true and I knew it was true. Sorry about this. Okay, thank you very much. Thank you.
Sure. Yeah. So because we are interested in global sections, so of course for holomorphic things, global sections are too few, so it's not good. Okay, but we can still do something using global sections. So a holomorphic, that is Koszul-Lagrange theorem. So a holomorphic vector bundle over a complex manifold equivalent is the same to say that we have a C infinity vector bundle together with a D-bar connection. D-bar means it satisfies the labeless rule. And together with a D-bar connection such that the D-bar connection satisfies D-bar E composed with D-bar E equals to 0. Okay, so, and with this, together with the Zhaoting theorem, we will be able to study holomorphic vector bundles over complex manifold globally using modules together with a D-bar connection, with a flat D-bar connection. And in this sense, again, holomorphic transition functions are no longer needed for the study of complex, for the study of holomorphic vector bundles of a complex manifold. So this opens the gate of the study holomorphic vector bundles in the non-commutative framework, in the framework of non-commutative geometry. Okay, is there any other comments or questions so far? Okay, if there's no question, then let's go a little bit more. Koszul-Lagrange theorem is for a single holomorphic vector bundle. And if we're talking about complexes of holomorphic vector bundles, then we see that is also quite straightforward. A complex of holomorphic vector bundle corresponds to the following data. First is a Z-graded C infinity X modules, which are bounded and finite generated projective. And we have a D-bar connection on each component, and we have a map delta, which is the differential of the complex, such that they are compatible. So, and moreover, the composition equals to 0, delta plus D-bar. Composed with delta plus D-bar equals to 0. So let me explain in the following picture. A complex of holomorphic vector bundle corresponds to a so-called double complex of C infinity module, C infinity X module, the delta corresponds to the differential of the complex, and that's the horizontal map. And the vertical map corresponds to the D-bar operator that gives the holomorphic structure on each component. And we have several points. For example, this delta should be compatible with the holomorphic structure. So that's the diagram commute. And the vertical composition gives 0. That is the flatness condition of the D-bar operator. And the horizontal composition also gives 0. That's the condition on the cochain complex. So altogether, it gives one equation, the delta plus D-bar composed with delta plus D-bar equals to 0. So notice that we put a plus minus sign on each D-bar to make it to be summed to be 0. So instead of the difference equals to 0. Okay, so let's look at the picture again. Okay, so we have this double complex. So this is the same to say complexes of holomorphic vector bundles on X. But we notice that so far we cannot study coherent sheaves in general. Yeah, but because we can only study so far, we can only study complexes of holomorphic vector bundles. That's a little bit far away from coherent sheaves. Okay, is there any questions so far? Any other comments? Okay, the study of coherent sheaves. One way to study coherent sheaves in the same framework is to use the so-called Z-graded connection. Okay, so what's this? First, we'll consider a differential graded algebra. In this talk, we most focus on the double differential graded algebra. And a Z connection. So let's E dot be a Z-graded A0 module. A Z-graded connection is a k-linear map from the tensor product to the tensor product of total degree 1 and satisfies the labelist condition. And yeah, this definition may be difficult to understand. So let me give illustration. A Z connection is determined since it satisfies the labelist rule. So Z connection is determined by its restriction onto E dot itself. And it can be decomposed into a lot of components, E0, E1, E2. And for each EI, it maps E dot to E dot plus 1 minus I tensors A0 tensor AI. And except, so EJ, all EJ are A0 linear except the E1. E1 is a ordinary connection. And so actually some authors use the term super connection, and we use the term Z connection to distinguish Z graded with Z2 graded. So let me explain a little bit more. What does Z connection look like? I think, stop, go out. Whiteboard. So ordinary, a connection means we have a module, say E, and connection, ordinary connection. On a differential graded algebra, if we have A dot and dA, what is ordinary connection? An ordinary connection of A0 module and A0 module E is a map like delta E go to, I think, E 1 over A0. that is an ordinary connection. Also satisfies the Leibniz rule. Delta, I use the right module. So delta E times A plus E times dA of A. So this in 0, 1. Okay, that is a connection, ordinary connection. Z-graded connection. Z connection or Z-graded connection means we have, instead of a single A0 module, we have a lot of Z-graded modules, a lot of A0 modules. E0 is a graded A0 module. So what is a Z connection on it? First, we have this both E1, that is each EI go to EI, hence A0, A1. But we also have one before and after that. E0 is each EI go to EI plus 1, and E2 is EI go to EI minus 1, hence A0, A2, and E3 is EI go to EI minus 2 times over A0, A3, etc. We have this. The first one is E0, but in general, we don't have the last one. It can go forever and ever. Okay, so the E1 term is the ordinary connection, and all other terms are actually A0 linear. So that is the definition of Z connection. And we have a picture illustration of it. So first, is there any questions so far about this part? Any comments? Okay, if there are no questions, then let's go back to the slides. Okay. Yeah. This is a picture illustration of a Z connection. This means that, okay, so the E0, EI go to EI plus 1, that's usually the horizontal part. And E1, EI go to EI times to A0, A1 is the vertical part. The point for Z connection is we have higher terms go to the other direction, E2, E3, etc. The total degree is 1. So the image of EI is always on this line, with the same total degree. Yeah, but we have infinitely many components of this connection EI. Okay. And what is a cohesive module? So, cohesive module is defined by Jonathan Block in about 2010. That is a Z connection on a graded module, and there are two requirements. First, the graded module is bounded and finally generated and projective. And second is the Z connection is flat, satisfies Z composed with Z equals to 0. And further, we can define morphisms between two cohesive modules, but in this talk, we don't need too much details about the morphism. So anyway, cohesive modules with morphism is actually a differential graded category. And let's have a closer look at the conditions E compose E equals to 0. So actually, this one single equation has infinitely many components, just as E has infinitely many components. The first component is E0 compose E0 is 0. The second component is E0 composed E1 plus E1 composed E0 is 0. And the point is we have higher components and they are all 0. And intuitively, we say that the E1 connection is flat up to cochain homotopy. I think we can see it from the third equation above. The E1 composed with E1 is the composed with this ordinary connection. We see that if it was flat, then this means E1 composed with E1 is 0. But however, this E1 composed with E1 is not 0, but this part equals to E0 composed with E2 plus E2 composed with E0. Sorry, maybe minus because we put a negative sign of it. And we see that the E0 is the differential of the cochain complex. So E2 is the homotopy operator. So we can say that E1 composed E1 equals to negative E0 composed E2 minus E2 composed E0. So this E1 is flat up to cochain homotopy. Okay, so let me see if we have a picture to illustrate it. Maybe, yeah, maybe later. So there's a picture illustration of it. We can see it more clear. And the point for this thing in complex geometry is if we take the differential graded algebra to be the double DGA, double differential graded algebra, then in this case, the differential graded category of cohesive modules on the complex manifold X exactly gives a differential graded enhancement of the derived category of the bounded derived category of coherent sheaves on X. So in short, we can say that any coherent sheaf corresponds to a cohesive module, and which is unique up to homotopy equivalence. And let me give an illustration in the next page. So what is a cohesive module in our complex geometry? That is very similar to a complex of holomorphic vector bundles. The difference is the same thing. The similarity is we have a complex of projective modules or C infinity vector bundles. And we have this horizontal differential corresponds to the differential of the cochain complexes. And we have the vertical differential corresponds to the d-bar operator. And there are differences. First, we have these higher terms of the differential, like E2, and actually we may have E3 and so on. And the second point is, instead of requiring the d-bar operator to be flat, E1 composed to E1 equals to 0. That was the original requirement. But here we just require that the E1 composed to E1 is flat up to cochain homotopy. That is, the E0 is the differential of the cochain complex, and this E2 is the homotopy operator. So E1 composed with E1 is equals to this and this. It's just flat up to cochain homotopy. And of course, this E2 need to satisfy higher compatible relations with E3 and with E0, E1, E2, E3 that satisfies higher coherent relations and so on and so on. Okay, so this is the illustration of cohesive module. Just compare it with a very previous picture of a complex of holomorphic vector bundles. We see that they're very similar. The only difference is we have higher terms and we weaken the flatness condition. We weaken the flatness condition. We only require it to satisfy flat up to homotopy. And the point for Bloch's result is with this flexibility, a little bit more flexibility, we can use cohesive modules to represent any coherent sheaf and actually bounded complex of coherent sheaf on a complex manifold. And actually, this result holds for non-compact complex manifold too. So block only proof is for compact complex manifold, and recently it's been generalized to non-compact case with slight modification. Okay, is there any questions so far? Any comments or questions?
One question, can you just confirm what you mean by DG enhancements?
Yeah, DG enhancement. Yeah, so let me just. Yeah.
Like you're enriching over DG.
Yeah, yeah, I think we still have enough time. So let me briefly talk about what is DG enhancement. So DG, so let's T be a triangulated category. I think you know what is a triangulated category.
Sure.
Yeah.
Category.
So, and A be a DG category. So first we can define the H0A is a ordinary category. Defined to be object of H0A is the object of A itself, but the morphism H0A X Y is the morphism of XY. This AXY is a cochain complex. That's the definition of DG category. And H0 means we take the zero cohomology of this cochain complex of AXY. So that is the morphism in this H0 category. Does it make sense? So let me. This is a cochain complex. That is the definition of DG category. That means any morphism is not a set. Instead of a set, it's a cochain complex. And we take the zero cohomology of this cochain complex. That gives the morphism of this new category. Okay, so what is DG enhancement? We say A is a DG enhancement of T if H0A is a triangulated category and of course H0A is equivalent to T. That is DG enhancement. Intuitively, this means that the DG category encodes all information of the triangulated category. Okay, does it make sense?
Yeah.
So there's another point. So that is usually the triangulated category T is the derived category of some category. So the difficulty of derived category is we need to formally invert the quasi-isomorphism. So that's usually the tricky part of derived category. In other words, it's not enough to just take homotopic invertible maps. We need to invert the quasi-isomorphisms. And the good thing for the H0A, the DG enhancement, is actually we only need to worry about homotopies between morphisms. So there's no, anything which is quasi-invertible is homotopic invertible in A. So that's the good point for this DG enhancement. So actually, if we can find the DG enhancement, a lot of theory will be much easier.
Okay, thank you.
Yeah, sure. Okay, so go back to the slides. Okay. There's a little digression. Is of course we can think if we are consider a real manifold and consider the RAM DG algebra, then what we get. So actually, there is a result also by Bloch and Smith. That is, in this case, if we consider a real manifold with the RAM algebra and we do consider the DG, the DG category of cohesive modules, with this the RAM algebra, then we get the DG category of complexes of course, C infinity vector bundles on X with flat super connection, with connection which is almost flat. That's the same as before, flat up to Cauchy homotopy. And and they even construct a so-called higher Riemann-Hilbert correspondence between this complex of vector bundles or flat super connection with so-called infinity local systems. So that's their construction. So we know Riemann-Hilbert correspondence is correspondence between vector bundles with flat connection and representations of fundamental group. And their result is vector bundles with flat super connection corresponds to the higher representations of infinity fundamental groupoid. That's a higher version of Riemann-Hilbert correspondence. Okay, so that's the second part of our talk. The third part is how to use the idea of cohesive modules to study determinant line bundles. The result is, the construction of determinant line bundle is surprisingly easy in the framework of cohesive modules. So that's what I get this small result last December, actually. So if we have a cohesive module in the framework of complex geometry, then we take the alternative tensor product of the determinant vector bundle of each of its components. Then the point is it has a flat D-bar connection, which is induced by the E1 component of the cohesive module. That's the Z-graded connection. And moreover, the new definition is compatible with the old definition. That means if E dot E corresponds to a coherent sheaf, then the newly defined determinant E dot is canonically isomorphic to the original definition using gluing and piecing. Okay, so how to prove this? The proof is surprisingly easy. So first, we know that this construction, determinant EI tensor with negative 1 to i's. So why we can do this? Because each EI is finitely generated projective C module over C infinity X. So they are just finite dimensional vector bundles on X. So we can define the determinants in vector bundle and tensor them together. The only difficulty, the only point is whether this the tensor product in the right-hand side, is it holomorphic or not? So in the framework of Koszul-Margrange theorem, the point is that the only thing we need is, do we have a flat D-bar connection on the right-hand side? So that's the only thing we need to prove. Page down. Yeah. And the answer is yes. The point is, so first, the notation is we just restrict to each EI. We just use this E dot I to denote the restriction. And as I said before, the E1 I is the connection part on the component EI. So it's an ordinary connection, not necessarily flat up to homotopy. Then according to the formula before, we can compute the curvature of E1 is given by the third equation before. The curvature of E1 is actually negative E0 composed with E2 minus E2 composed with E0. So therefore, the curvature on the determinant line bundle is just given by the trace. So it's -1 to the I because we transfer -1 to the I. It's -1 to the I trace E1 composed with E1 is -1 to the I trace E2 I plus 1 E0 minus E0 I minus 1 E2. Okay, so this thing is not 0, of course. Yeah, so which means on each tensor component, the E1 is not a flat debug connection. However, after we cancel all them together, the curvature of the total induced debug connection is the sum of them. And since we are taking trace, we see that E2, E0 in the previous component and E0, E2 in the next component, they get canceled. So if we take sum, the sum is 0. So this means that the E1 also is not a flat connection on EI or determinant of EI themselves, but on the tensor product of EI, magically they canceled, so the result is a flat debug connection. So we get a canonical holomorphic structure on the determinant line bundle. And the second component, the second part of the statement is just study the definition, untangling the definition of what we mean by the cohesive module corresponds to it. So to study this correspondence, we can show that our new definition is coincide with the old definition. Okay, so in other words, to define the determinant line bundle of a coherent sheaf, we no longer need gluing the local definition and gluing. We can just simply define it in the framework of this cohesive module. It's very non-commutative geometric. So we see that non-commutative geometry, I think the most important strategy is to use globally defined functions to replace local data. So we see that we can do everything globally. This is the determinant line bundles in the framework of cohesive modules. Okay, so it seems that we are hitting a very small nail using a very big hammer. But I think at least this shows that the framework, the cohesive module framework makes sense, is quite promising. So then let's talk about something I'm considering is interesting as a non-trivial further applications is the Quillen's study of determinant line bundles. So in a celebrated paper of Quillen, he considered complex Riemann surface and a fixed C-infinity complex vector bundles on M. And he considered the space of all D-bar operators. I think there's there's all D-bar operators. And I think the third point is not any D-bar operator. He considered flat D-bar operators on E. And Quillen defined its determinant. And the determinant is a vector space, but Quillen pieced them together to obtain a globally defined holomorphic line bundle on the space of this parameter space of D-bar connections. And he showed that this vector bundle is holomorphic, and he defined a Hermitian metric on this line bundle, the Quillen metric, and he computed the curvature, and he also constructed a non-trivial holomorphic section of this line bundle, which has a lot of consequences in geometry and even in physics. Okay, however, Quillen's definition, of course, is commutative geometry. He defined the line bundle globally and he pieced them together, and he defined the Hermitian metric locally and he pieced them together. He showed them, he showed that on the overlap of two local chats, they coincide and so on. It's very commutative geometry. In a recent paper in 2017, not very recent, the authors, I think, 2017 paper is Fathy, Gobanpo, and Kalkari. Yeah, they use non-commutative geometry method to get the similar result on non-commutative two tori. He replaced Riemann's surface by a non-commutative two tori, and they obtained the similar result. Of course, their result is, their method is in non-commutative geometry. They no longer use local chats and things like this. And one interesting thing in my mind is Quillen considered a fixed complex vector bundle and then different structures of d-bar operators on it. Using the framework of cohesive modules, we can hope that we can do the same thing to replace a vector bundle by a complex of vector bundles, and yeah, we can also study the determinant line bundles on the parameter space of these complexes of vector bundles. It will be very interesting. Okay. And other maybe future direction of work, maybe Kobayashi hitching correspondence for coherent shifts. Yeah, that is because for coherent shifts, there's a correspondence between the so-called stable coherent shift and the so-called Hermitian-Einstein connection on holomorphic vector bundles. Sorry, not stable coherent shift, stable holomorphic vector bundles and Hermitian-Einstein connection on holomorphic vector bundle. So that's the so-called Kobayashi hitching correspondence. And so as I said, we can actually define stable condition on coherent shifts. So we can hope that we can also define the Hermitian-Einstein connection on the corresponding cohesive modules and find the same correspondence. And maybe other direction, the second topic maybe is the real geometry case. You can study flat superconnections and analytic torsions. So actually, some people already study them, but their framework are still local definition and glue together. So I hope that we can just do the same thing globally. And the third topic may be purely non-commutative geometry. So could we do the same thing just on some genuine non-commutative space, like quantum projective space, quantum Fleck varieties? Yeah, I think in the audience, there are a lot of experts on this. That's something maybe interesting in the future. Okay, I think that's my talk. That's it for today. Thank you.
Hey, Will, thank you very much for a very nice talk. Do we have any questions from the audience? Then I'll ask, I mean, just, it's not really a question, more a comment, but from what you're saying, I mean, the way that you set everything up, seems that it should be possible to extend it maybe to something like the Podle sphere to start with. And then maybe up to the Fleck manifolds. It seems possible.
Yeah, I hope so. So, but so far there are very few work done on the genuine non-commutative space. I think Bloch did some work on non-commutative tori, but beyond that, there are very few things done.
Ramon, I think that in the treatment that is available now, these objects are perceived as quantization of their algebra of functions, and for this algebraically, and I'm not sure that what Wei does holds algebraically. I mean, does it hold? Because the Zariski topology is very different from the complex one. What do you say?
Could you say your question again? Could you say your comment again?
So what your results, do they hold in a purely algebraic setting where you are considering topologies?
You mean the purely algebraic setting? Then what do you mean by algebraic? So because do we have the bold algebra in the purely algebraic setting?
Yes, you do, but the problem is that your open sets are not as friendly as the complex ones.
Yeah, that's a good point.
And Ramon, in the world of non-commutative geometry, we know very well that we don't have many abundance of open sets, right?
Yeah, that's true. Yeah. So far, I'm negative about this. Yeah, I don't think.
Me too.
Yeah, because
I don't see right away how you could do that, and for this reason, I'm a bit skeptical that this could have an easy generalization to quantum. But maybe I'm wrong. That is possible.
Yeah, maybe. Yeah, that is the question. But I'm not sure. Quantum projective space. Yeah. Also, the difficulty is, I think, so far, it's difficult to describe what are the so-called C-infinity functions over quantum projective space. We only have a set of generators of functions on quantum projective space. So so the starting point is the Serre-Swan theorem, but do we have that for quantum projective space? And Serre-Swan and Kouzou-Lagrange. So if do, then it's quite promising to proceed. But if we don't have that, then of course the whole thing.
So it worked with Adam and Jan. I mean, what we were able to do was to take category of, how was it, they were finitely generated, finitely presented modules over the quantum projector space, over the algebraic functions. You equipped them with a connection. And then you took the category of this basically. The category is too big. So then you look somehow at the category generated by the line bundles inside. Gave you a realization of the coherent sheaves. We were able to show that this was equivalent to the coherent sheaves where it's going to be the Hugger of the homogeneous coordinate ring in quantum projector space. So it seems all to be quite close philosophically, at least to what you're doing, but
but we don't know how close they are. That's why it's difficult. So anyway, the tori case maybe is within our reach. Yes, maybe in the near future we can do it. The tori case, but the quantum projective space that's a really interesting part, I think. But more difficult, much more difficult.
Okay, so are there any other questions? No, I think that might be it. Okay, so in that case, let's thank Zhaoting again.
Right, thank you. Thank you.
And so next week we'll have another, this is swinging back to the more C-star algebraic interest of the seminar. This is from Marzia Foro here in Prague in the Czech Academy of Sciences. And the title of the talk is Lifts of Completely Positive Equivariant Maps. And the abstract is available on the website where you can have a look. So hopefully we'll see you all there next week. And thank you again for attending.
Okay. See you. Bye.